Welcome to Chapter 1 of the Graph Neural Network series. In this lecture, we'll explore the fundamental concepts of graphs, the mathematical structures that underpin everything from social networks to molecular structures. By understanding graphs, you'll gain insight into how relationships between entities can be modeled computationally. By the end of this chapter, you'll be able to create, manipulate, and analyze graphs using Python. A graph is a mathematical structure that represents relationships between objects. Formally, a graph G is defined by two sets: V, the set of vertices or nodes representing entities, and E, the set of edges representing relationships between those entities. This simple yet powerful abstraction appears everywhere. Social networks where people are nodes and friendships are edges, molecular structures where atoms are nodes and chemical bonds are edges, road networks where cities are nodes and roads are edges, and knowledge graphs where concepts are nodes and relationships are edges. The beauty of graph theory is that the same algorithms work across all these domains. Graphs come in two fundamental flavors, directed and undirected. In an undirected graph, edges have no direction. If A is connected to B, then B is also connected to A. Think of Facebook friendships. If you're friends with someone, they're automatically friends with you too. In a directed graph, edges have a specific direction, like arrows. Follow relationships on a platform like X, formerly Twitter, are a perfect example. You can follow a celebrity, but they don't have to follow you back. This distinction matters because it affects how information flows through the network and which algorithms we can apply. Directed graphs can also have cycles, where you can follow edges and return to where you started. Let's explore the different types of graphs you'll encounter. A tree is a connected graph with no cycles. Think of file systems or organizational charts. A DAG, or directed acyclic graph, has directed edges but no cycles, perfect for representing task dependencies. A complete graph has edges between every pair of nodes, useful for representing fully connected networks. A bipartite graph has two distinct groups of nodes, where edges only connect nodes from different groups. This is the structure behind recommendation systems, connecting users to items. A cycle graph forms a single loop, while a regular graph has every node with the same number of connections, like atoms in a crystal lattice. How do we store a graph in computer memory? The most straightforward way is an adjacency matrix, a square matrix where rows and columns represent nodes and entries indicate edge presence. For a graph with V nodes, we create a V by V matrix. If there's an edge between node I and node J, we put a 1 at position ij. Otherwise, we put a 0. For undirected graphs, this matrix is symmetric. For weighted graphs, we store edge weights instead of ones. The adjacency matrix makes checking for edges very fast. Just look up the matrix entry. However, it uses O of V squared memory, which becomes problematic for large, sparse graphs where most entries are 0. For sparse graphs, we have more efficient representations. An edge list is simply a list of all edges as pairs of nodes, A to B, A to C, and so on. It's compact, using O of E memory, but checking if a specific edge exists requires scanning the entire list. An adjacency list stores, for each node, a list of its neighbors. Node A might have neighbors B and C, node B has neighbors A, C, and D. This uses O of V plus E memory and makes finding all neighbors of a node very fast, which is exactly what we need for graph traversal algorithms. In practice, adjacency lists are the go-to representation for most graph algorithms, especially on large, sparse networks. NetworkX is Python's standard library for graph analysis. With just a few lines of code, you can create graphs, add nodes and edges, and run sophisticated algorithms. Import networks as NX, create a graph with nx.graph, and add edges with g.addEdge. NetworkX ships with hundreds of graph algorithms, covering everything from shortest paths to community detection. It supports directed, undirected, and multigraphs, handles node and edge attributes, and integrates beautifully with NumPy and Matplotlib for numerical operations and visualization. While it's not the fastest option for massive graphs, its ease of use and comprehensive feature set make it perfect for prototyping and analysis. Graph metrics help us understand network structure. The degree of a node is simply the number of edges connected to it. Highly connected nodes have high degree, but degree alone doesn't tell the whole story. Centrality measures capture different notions of node importance. Degree centrality is just normalized degree. Betweenness centrality measures how often a node lies on shortest paths between other nodes. High betweenness nodes are bridges in the network. Closeness centrality measures how close a node is to all other nodes. And PageRank, famously used by Google, measures importance based on being linked by other important nodes. Each metric reveals different aspects of network structure and is useful for different applications. How do we convert graph structure into features that machine learning models can use? Node embeddings solve this by mapping each node to a dense vector where similar nodes are close together. DeepWalk adapts Word2Vec for graphs. It performs random walks on the graph, treating the walk sequences like sentences, then trains skipgram to learn node vectors. Node2Vec extends this with two parameters, p and q, that control the walk behavior. The return parameter p controls backtracking. A low p makes the walk revisit the node it just came from, keeping it in a tight local neighborhood. The inout parameter q controls how far the walk strays. Q greater than 1 biases the walk toward nearby nodes, giving breadth-first-like local structure, while q less than 1 pushes it outward, giving depth-first-like exploration of global structure. These embeddings capture both structural similarity and neighborhood information, providing powerful features for downstream tasks like node classification and link prediction. Let's recap what we've learned. Graphs are mathematical structures representing relationships through nodes and edges. We can store them as adjacency matrices for dense graphs or adjacency lists for sparse graphs. NetworkX provides a comprehensive Python toolkit for graph creation and analysis. Graph metrics like degree and centrality reveal structural properties, and node embeddings like DeepWalk and Node2Vec convert graph structure into machine learning features. In Chapter 2, we'll build on this foundation to explore graph convolutional networks, which learn directly on graph structures without explicit feature engineering. I encourage you to practice by creating your own graphs with NetworkX and computing various metrics. See you in the next chapter.